Thank you very much, and good evening, everyone. Tonight, we look at how a piano works. In particular, I will tell you about modeling, which is what we do as engineers to understand, replicate things. I'll tell you about some measurements that we do on objects like trains, pianos, pianos, and we'll do some listening as far as we can do, and play a little game at the end. That's me, and also credits to Pablo, who has been helping me through the years in carry on the research in piano acoustics as a hobby. So that's fine. We can deal with the crackling. At the beginning, I'll tell you why a person like me, who by the way happens to be a mechanical engineer as a background, is into the acoustics of pianos and music. I will tell you what I mean with a model. What is a model? We look at how a piano works, so how a sound is generated when you press a key in a piano, and the different parts of it, hammer, string, soundboard, we'll get to meet them soon, and then a little bit about how they radiate sound at the end. And we do some listening at the end and some pictures to finish with what we are going to do next with all this knowledge. So science, engineering, music, why? Or in other words, why did I end up studying piano acoustics, being a mechanical engineer who happens to work on railway noise and vibration? Well, actually the beginning was long ago. When I was 9 years old, I started to play the French horn. Today is not about the French horn, but at 9 years of age, I had a question like, why when I play the French horn, I press one key and I can produce different tones? While on the piano, you press one key and you always get the same tone. And I thought that it was much easier to play the piano rather than the French horn, because then you could make so many mistakes when you play the French horn. If you play brass instrument, you know what I mean. That's exactly due to this, because you can get multiple harmonics from the same length of a tube. I didn't know it at the time. I asked my teacher and he said, those are silly questions, keep practicing, you get better. I kept practicing, I get a little better, but I also wanted to know about those things, so I kept those questions alive, and I'm here now talking about the acoustic of musical instruments. That's not the only reason why people like me study about pianos. There is interest in the industry, so piano makers, they are interested in engineering approaches to know how improve their products. For example, a piano manufacturer could ask, can I rely on engineering testing to verify the quality of the instruments? Or can scientists develop mathematical models that can replicate the sound of my pianos, and I can use to listen to how the piano would sound if I change something before I build a new piano that is very expensive. And this is how I started to do my PhD some time ago with an Italian piano manufacturer. Other questions, we are asking this right now. Can scientists develop virtual models of pianos that no longer exist, pianos of any other instrument, so that we can listen to how an instrument would sound 200, 300 years ago? And well, stay tuned. In a couple of years, maybe I'll come again and show you more about this. Now, engineering music, so there are connections we have seen. In the piano itself, there are parts of the piano that move with very high precision. That's the action of the piano. And the beauty of this mechanism required a couple of hundreds of years of refinement. This is how the action works. But also the physics of impacts and vibration of the strings is of interest to musicians because of the sound that it comes, but to also scientists and engineers to understand and improve what is happening when a hammer hits the string vibrates, and the pulses, they travel in the string, and this is what eventually will make the sound that we hear. The manufacturing process also requires a lot of technicalities, engineering, design, and processes. In this little video, you see how they manufacture the soundboard of a piano. I will talk about the soundboard in a minute, but you see here that this process doesn't seem to have anything to do with music, but they are making a piano. Okay? So I wanted to start with this to give an introduction to why there is an interest in a person like me, mechanical engineer, in piano acoustics. I hope I've given myself enough excuses to carry on with the work on pianos. All right? Modeling. So the first thing I wanted to address is, well, what do I mean with a model? What is a model? Well, a model is just a representation of something, a simulation of a system, a process, a concept. And in our case, the model could be something that answered the question, how does the string vibrate when it is struck by the hammer? You hit the string, it vibrates, produces a sound. How does it work? Can a model explain this phenomenon? But also the model, back to the beginning, can help engineers or piano manufacturers to design and optimize solutions before implementing them. So, like before, how does the sound change if I change this parameter in the piano? The length of the string, the tension, the thickness of the soundboard, the curvature of the soundboard, and so on. So those are what the models do. What do the models require? Well, in our world, models require a set of equations and a way to solve those equations. Equations can be something very simple. Most of you might have seen at some point in their life this equation, which is the famous Newton's second law, F equal ma, where F is the force, so that push that you give to an object. If the object has a certain mass m, the object will experience an acceleration, so a change in the velocity, which is proportional to the force and inversely proportional to the mass. That's Newton, the guy who postulated this, and you might have heard of the story of the apple. The apple didn't fall on his head, but there is an apple tree in his garden. So there must be a connection with the apple. All right, so let's push an object. Apply a force, and the object moves. The model not only can show us that it moves, but can tell us where exactly the object is at any given moment in time. Fair enough. So engineers apply this rule to study how train moves, not this train, vehicles, airplanes, or pianos. Okay, now you're thinking, this guy is pushing pianos. He must be part of a piano removal company and is here to advertise that. That is not the case. What I mean with F equal ma is that we apply this equation and the other variations of it to all the parts that are within the piano, so that we can study how they move, they collide, interact, eventually producing the sound that we hear. So let's start. The first thing we want to, by the way, for the piano, F equal ma, well, can become a bit more complex. This is not your problem, it's our problem, it's Pablo's problem. Okay, so let's get started. I showed about the action. For the action, it's actually a very beautiful mechanism, but we need to leave it aside for today. Otherwise, we spend the entire evening on the action. But the idea is that there is a complicated mechanism that converts pressing the key into the hammer hitting the string. That's good enough for us. What I'm more interested in is in what creates the vibration and the sound, which is the hammer now hitting the string vibrating and being connected to the soundboard at the end. The first ingredient of this set of components of the piano, how it works, is the hammer itself. How do we put the hammer and how it moves into a model? Well, we need a model to describe how the hammer interacts with the string when the hammer hits the string. And we started with something simple. We took a hammer, this very hammer, it's a hammer of a piano, you can have a look at the end. And we did measurements. We measure what is the force exchange when the hammer is a surface that resembles a string. When this happens, we know from what was known well before us that the hammer is deformed a little at the head, and this deformation, so how much is pressed by the string, well, it gives us how much force is exchanged between the hammer and the string. Okay? And then there is an equation that can describe this. F, the famous F of Newton's second law, in this case has a certain relationship with how much compression is there. Now this relationship can be simpler or a bit more complex. Those are just models, don't worry for that. What we need to do, however, is to see how the model behaves, and this is a result from the model. You see, we simulate the push and we get the force that the hammer gives to the string. But then even if we have a model, we need to make sure that the model is correct. Is it valid to describe this phenomenon? So how can we decide what values to give to the different parameters of the model? Or if there are different models, which one is the one that works best? Well, to do that, we need to tune our model and to validate the model with the measurements. So we did the measurements, and here is a little video where you see what I mean we did the measurements. We literally made the hammer hit a surface that is equipped to measure the force that it sees when it is struck by the hammer. There you go. We get this pulse of force. Okay? Now we have the model that is doing something similar. The measurements are doing something similar. We need to compare the model with the measurement and tune the model. When we start, they look similar in shape, but not well aligned. But now we can tune the model. We can change the parameters of the model until slowly, we get to an agreement that is good enough for us. Then we could question, well, there are still differences. And then we say, okay, maybe we need to fix this difference. We could try with a more sophisticated model and see if that little difference is adjusted. It is adjusted. Overall, we now know it makes a very, very subtle difference in the sound that would make, but we are able to put it into our model, have it there as an ingredient to study what is the effect of this. Okay, there are other complications of the hammer that I will not go into the details too much, but we also realize that the hammer behaves differently when you press it from when you release the force. And some models can account for that behavior. Fair enough, move on. The hammer is sorted. Welcome the strings. In the piano, we have seen in the animation, the hammer is the string. Now we need a model for the string and how they interact with the hammer. Again, there are mathematical equations for the string, kind of F equal ma, but again a bit more complicated. Still none of your problem. There are ways to solve those equations, and the computer is helping us very much. To understand how the string behaves, I think it's best to start with an animation. Well, more than animation, a proper demonstration. Well, now imagine this being the string. Okay? Now, forget the piano for a minute. The first thing you notice when you have a string and you make it vibrate is that it can take different shapes of vibration depending on how quickly you shake it. So we call this the vibration modes of the string. So earlier we had the stop it. Yeah. So earlier we had this is the first vibration mode, and if I more or less double the frequency, I get the second vibration mode, and so on. I'll try to get the third vibration mode. Stop it. There you go. Okay, so these modes exist in the string always. They are a property of the string. When the hammer, that's too small. When the hammer hits the string, all these modes, they are excited. And they all contribute to the vibration of the string. To the point that, if I do it, I actually get a pulse going back and forth. Believe it or not, this is the combination of all the modes that are there in the string. And as a consequence, when we listen to the sound, we don't just hear this mode or this mode. We can hear all of them. But one of them is the one that defines the fundamental pitch of the tone. Okay? So we'll go back to the slinky in a few minutes for another demonstration. But it's important to put this in our knowledge, so we know about the vibration modes. Those vibration modes are hidden in this equation. They are there. We can represent them when we solve the equation. So that if we do an animation from the computer of what we have done, and we imagine that we hit a string that would only have one mode, that's something you couldn't do in reality. They are all there. But one mode only, well, it would vibrate like the one mode only. But if we start to add modes one by one, so we imagine we have two modes, we start to see that something is actually moving. Look at the four modes. Something is traveling to the other side and then is reflected back. Well, let's put all the modes. Look at what we see. It's traveling and coming back. If you remember the video I did at the beginning, here, I'll play it again. Look at the right video. When the hammer is the string, there is a movement, then it seems silence. What is happening is that the pulse is traveling and then it's coming back. And it does it very quickly. It can do it 40, 50, 100, 1,000 times per second. That will give us the tone that we hear. So the sound comes from this pulse traveling and bouncing back and forth in the string. All right. So this is how the string reacts to the hit of the hammer. However, things are not so simple. Because, well, we don't live in a one-dimensional world or bidimensional, that things can only go up and down. When you hit the string, because of imperfect striking or the connection with the soundboard, the string can do this, but of course could also do this. So these modes, they exist in the vertical direction or in the horizontal direction. But, very importantly for the piano, these modes also exist in the longitudinal direction. So it's a bit short, the stage, but I think you can see it. Can you see the pulse traveling? And this pulse travels at a different speed than this. And this adds color to the sound. We will try to listen to the audio files with and without this effect. And this is a very important part of how the piano sounds. I'll show you it in a minute. But now we know about the vibration modes. They are all there. They can be vertical, horizontal, also longitudinal. And they all have some contribution to how the piano sounds. Okay. We've done the hammer. We've done the string. The string at one end touches the soundboard. And one of the studies we have done recently was to ask ourselves, from the point of view of this pulse traveling the string, is the soundboard a rigid wall that only reflects? Well, of course we know that the answer is not. The soundboard is actually not a rigid triangle. It's a very nice piece of wood. that takes months to manufacture because it needs to be, well, found, cut, glued, seasoned, and so on. Okay, so and this object itself can also vibrate, and it is in fact the reason why we hear the sound. It vibrates like the membrane of a speaker and it radiates sound into the room. The way the soundboard is manufactured is also very fascinating. You have seen already a video. What they do, they take the main board, they need to stiffen the board because when they tension the string and they press the string onto the board, overall, in grand pianos, they get something like 200-300 kilograms of downforce. So it needs to be a very solid structure to sustain that load, but also flexible enough to vibrate and radiate sound. It's a big challenge that is solved by gluing stiffeners or ribs on a curved mold so that when the load that is pressing down while the glue dries is released, the soundboard preserves some curvature. By analogy, and forgive me the poor analogy, but I thought this was a good demonstration, it was like this. If you imagine this part of the bow being the soundboard and the string being the stiffeners, when they are pressed and then released, they exactly give this effect. The soundboard is slightly curved. Slightly curved is good because it can take the load very well. While the stiffeners, they are slightly tensioned. And that helps overall the structure to be stable, but also radiate sound well. All right? And then the process goes on, and then here is the soundboard at some point of the manufacturing process. All right, so once we have a soundboard, if we have one, what can we do with it? Well, you know the story of the hammer, the model, the measurements. In this case, in my approach to piano acoustics, I started with measurements. We had connection with this piano manufacturer. We were given soundboards that we could test. So we started to measure how the soundboard itself vibrates, how flexible it is, and how then can we connect this flexible object to the string. When we do measurements of this type, we measure how easily the object vibrates at the different frequencies. So we produce figures like this one, where the peaks, they correspond to the resonances of the structure. So those vibration modes, they will result in a resonance. The string has its vibration modes, the soundboard has its vibration modes. Like this. They are more complicated, very difficult to visualize, but in a model, again, we can look at them. All right? But if this is the frequency identity card of the soundboard, which says how flexible it is, how does it compare to that of the string? Well, like this. So, not much flexibility for the soundboard, so it's quite rigid. A lot of flexibility, particularly at the resonances, for the string. Now, we have a model of the hammer, we have a model of the string, we know something about the soundboard from the measurements. To close the story, we would want a model of the soundboard, so that we have a model of everything in the piano, and we can solve the equations and make the model produce some sound and see how it works. Well, the next step would be to make the model of the soundboard. Making a model of the soundboard is rather complicated. We did several tries. One of them included replicating the manufacturing process of the soundboard. So here in the animation you see a finite element model. If you know what it is, it's just another way of solving equations where we are replicating the manufacturing process. You remember the stiffeners were glued under pressure on a curved surface, and here you can see that slowly we're pressing down in the model the stiffeners to reconstruct exactly that correct curvature, so that we get the correct behavior of the soundboard. Not only that, we also need to replicate how the structure is arranges itself when the pressure is released, and then the model can also do that. And at the end we end up with a mathematical representation of the soundboard. In this case, is a rather complicated one. Maybe we were overdoing here, but at some point you need to try and see. If it is too much, you can simplify the model. If it is too little, you need to add details. Okay? When you have a model, again, for the sample, you need to ask yourself, is the model valid? We have the measurements for this frequency identity card of the soundboard. We have the model, and in this case, they match pretty well, not as well as the hammer, but forgive me, this is a much more complicated structure. The model struggles a bit. But overall, in this context, is a rather good comparison here. So, we did the hammer, we did the strings, we also did the soundboard. What we need to do is to put them together, and that complicated set of equations I was showing at the start is doing exactly this. It's taking the three components, the characterization of the three components with the equations that represent them, and by solving them we can find out what forces they exchange, how much they vibrate, and then eventually what sound they produce. Let's have a look at how the full model as a slow down animation works, particularly how is the solution when we hit the string, this blue string, with the hammer. I need to press it again. And now we will see the hammer hitting the string. There you go. The pulse travels, it finds the soundboard, mostly is reflected, but a little travels beyond the soundboard. For those who are familiar with pianos, this segment of the string that is the other side of the soundboard is called the duplex scaling segment. And in some good pianos, in some notes, the high register is tuned to resonate in accordance with the higher harmonics of the longer part of the string, this one here, which is called the speaking length. Who was making the example earlier? Someone was talking and he was saying pianos are, the real pianos are tuned and refined like a Formula One vehicle, right? So that every single detail is adjusted up to the point that the player of that day would like it. There were some famous pianists that were going on stage or on tour with their own tuners because they wanted to refine some details before the performance. Our models are not so refined to replicate that. We are learning slowly. But this inclusion of the duplex scaling segment is a detail that our model can do, that is adding a little subtlety to the many subtleties needed to replicate the total behavior. All right, we've seen the model. Let's try to look at some, listen to some example sound of what the model can do, and I will make it a journey of increasing complexity so that we try to appreciate what small changes can result into. Now let's start with something very simple. We were telling earlier about the presence of many vibration modes in the string and the fact that they enrich the sound. So we can still hear one pitch enriched by all the harmonics. In a model, just to understand what it means, we can remove all the higher modes and have a piano with only one string and one mode. It would sound like this. Let me practice finding the mouse. This side. There you go. Not quite a piano. Okay? You didn't come here to listen to this. No. Okay. So one tone, very boring. It's a pure tone. Okay. The piano is not like that. Oh, I knew it. Right. The actual tone, we said, is enriched by higher harmonics. There are multiples of the fundamental pitch. I was telling earlier, I do one frequency, I double the frequency. If we had a perfect sequence of harmonics, then the piano would sound like starting to get closer to what a piano would sound like. But there is another subtlety here that I didn't mention yet. The sound we've just heard is made by higher harmonics that are perfect multiples of the fundamental. So fundamental frequency times 2, times 3, times 4. Well, in reality, the piano string is not that perfect. It's a steel wire that is not really a string, but it has some bending stiffness, we say. And this bending stiffness shifts the higher harmonics a little, and the sound changes a little. So I'll try to play the two again so you might be able to hear the difference. So an ideal string would sound like this. A normal piano string would sound like there is a change in the tone. I knew it wouldn't be so audible, so I exaggerated that. If we exaggerate that, it starts to sound more like a bell. So the real string is not pure, it's not so imperfect as a bell, but is imperfect enough to make the sound more interesting than the pure one, but still pleasant enough. Okay? That's the first detail that we can look at. There are other details. Let's try to add them. We were doing earlier the demonstration. The string can vibrate vertical or horizontal, and the horizontal vibration will contribute to the sound. Now, what I'm going to do here, I will play. That's not a very efficient way of playing. Give me a second. I press this. I'll do that. And I'll do this. Let's see if it works. So I will play the sound that would come only from the contribution of the vertical vibration. Okay? But now listen to what would come from the lateral, so the horizontal vibration. Okay? So that's something that starts from 0, then it increases. That's the idea of this drawing. Why is that? Because initially we hit in the vertical direction, but then the string and the connection of the sample that is imperfect would shift the string to oscillate on the other side and again contribute to the sound to some extent. Another subtle details that is there in the pianos. And to this, not even this works. All right, this will work. Okay, so we can look at this in this animation. So on the top row, we look at the animation of the vertical direction, and you see now the pulses moving back and forth very quickly. In the second row, we look at what is happening in the horizontal direction. So slowly, the string is starting to vibrate in the horizontal plane. Then a bit later in time, the vibration in the horizontal plane has become the most important. It takes longer to decay. And that gives a certain characteristic to the piano tone that sometimes is called the double decay. So that at the end, the last one to vibrate is the transverse direction, is the horizontal transverse. Okay? So we've done vertical, and harmonicity, vertical transverse. You remember earlier I was trying to make the longitudinal contribution. That's an interesting one because this adds a lot of color to the piano sound. So if we include this effect in the model, let me do this. I think this will do the trick. I will first play what we already heard many times, the contribution of the sound from the vertical transverse. Okay, fine. What is coming from the longitudinal sounds like this. There's a ping, because that frequency associated to the longitudinal modes is much higher than the transverse. Okay, if we put the two together, subtle difference. I don't know if you're able to hear the ping hidden in the sound, but next demonstration will make you hear that, don't worry. Okay, now the problem of that ping in the sound is that, well, we cannot really tune it. That's a problem for piano designers, piano tuner, because of course you can tune the main transverse by changing the tension. That's also what you would do in a guitar, but you cannot change the longitudinal unless you change the length, and you cannot really, or you change the mass, and you can to some extent, because you see that some piano tones, they have an added wire all around made of copper that changes the mass of the wire without changing without changing anything to the main core of the string. All right? Some very good designers, and now it's in place, they found a way to design the piano overall, so to have those longitudinal modes at the right place, and to change that longitudinal frequency ever so slightly to demonstrate that, now you will hear it. So there are like two sounds hidden in there. Good enough. One is the main tone, and the one is that ping that unless it's changed from one to the other one, we would not even realize it is there. But it's always there. It is adding some color to the sound. It's very important to characterize a piano, or even to make difference between piano brands. They can tune those slightly differently to have a brighter sound or less bright sound, which is a characteristic of their pianos. Now our model can do the same. Might not be as audible as this, but I'll try to do a similar thing from the model. Some places it was audible. Did you hear it here? Because it was not there. Okay? While, not that one. Now it's only that effect. In a real piano, you cannot take them apart and listen to the two separately. In the model you can also adjust the relative level. And if I knew about the audio system here, I would have enlarged the longitudinal effect. I will skip this one because it won't be very clear, but I will do this one. So this same guy, sorry, I should have mentioned this person. He is one of the founders of piano acoustics. He was a piano designer, and he contributed to this book, which, if you are interested, is a very nice introduction to the piano acoustics. And when they did this book, they he prepared these audio files that I played earlier. I will play another one, and he managed to hide a melody in the longitudinal vibration of the string. Let's see if you can. Okay. So again, you hear the same note with the different frequencies of the longitudinal modes tuned to give a melody. So that demonstrates how important the longitudinal component is. I try to replicate the same in the model, well, with Pablo. Just about, you could hear this hidden there. Now, you may have realized from the tune that this guy was from the United States. Here we would play this one. That was hidden in there. Okay. In the real piano, it is very difficult to tune the longitudinal mode to do what you want. In the model, it's very easy. So the model can do what you want to do. I'll carry on with another subtlety, just very quickly. There are so many subtleties in the piano. I didn't mention this, I'll tell you now. Most of the piano strings, for the same tone, they come in pairs or even in 3 strings for the same note. But sometimes composers, they tell the players, use the una corda pedal. This means that they need to press a pedal that shifts the action, and then in that case the piano would only hit one of the 3 strings, or 2 of the 3, or 1 of the 2. Okay? We have done this in the model too. It won't be very audible, particularly here, but again, it's an effect that changes the color of the sound, particularly changes the color in time. Now, this figure here is a representation of the color of the sound, where you have the frequencies hidden in the sound and the time, so how the frequencies change with time. When we use the una corda pedal, you see that all the frequencies that are present, they decay almost equally with time. While when we hit 2 strings, as in normal playing condition, you see these blue lines there, they give a beating effect. So something does wah, 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 because of the interaction between the 2 strings. I'll try to play it. I don't think it will be super audible, but it is at least visible. But what I can also play, that in a real piano you cannot do, is to listen to what the string that is not hit by the hammer would do. Because even if it is not hit by the hammer, it's there next to the vibrating string, and it would vibrate by sympathetic vibration. Okay, so let's start with this. Let's listen to the una corda pedal effect. We listen to what comes from the string that is struck by the sound, by the hammer. Okay, similar to the others. But if I do the other string, the one that I've called the passive string, this does. Because again, initially it's not there because it's not hit, but then it contributes later on. Let's see if we can get those beating audible in the room. When we hit 2 strings, we get. Maybe you get the modulation in time. Okay? A number of subtle effects, all combined together, tuned to perfection, will give you the piano. The model is trying to take all of them, and it's quite difficult, and it's at the moment it's quite difficult to tune all of them to what we want to do. The last step in the model is to actually create a sound. What we have been listening so far, I've been cheating a little. We were not listening to the sound, we were listening to a sound synthesis of the force exchange between the string and the soundboard. There will be another step, which is to, well, separate the two, get this interaction force put it into the soundboard as a big vibrating plate, and then calculate how the soundboard radiates sound in the room. It's still very much work in progress in our research, but we got it started, and well, we can play a melody. So the virtual piano can play our first tune, which is not just repeating the same note, which I don't know why I chose this tune. Actually, I know why. This is to celebrate Southampton in Premier League. But now you tell me, no, we are for Portsmouth. No. All right. I'm nearly at the end. I just wanted to leave you with an insight of what is coming next. So, well, why are we doing what we are doing? First of all, to answer the question of the 9-year-old me who wanted to know how the French horn works, but that doesn't pay the bills. So we thought that as a next step, we want to modify our model to be able to replicate pianos that no longer exist or are no longer in playing condition. If we get to know enough about the details of those pianos, we can change all the parameters in our model and play or When the Saints or something else on an old piano. This is a piano that we have in Southampton, currently in my office, from David Owen Norris, and we realized that it's not so easy to look at how it's designed inside. This is a square piano, is how the pianos at some point evolved into this form and then they changed. But it's very difficult to make a model of the piano if you can look how the piano is inside. We found colleagues who can do that. You can do a CT scan of the piano, if it is small enough, of the whole piano, and literally look at how the piano was designed at the time. So then we can make our models, put the ingredients together, and well, it's really work in progress, just started. I don't have the sound samples yet, but the idea would be to carry on the research on early pianos. I understand we are getting very, very close to the end. Maybe to promote some thoughts and some questions, I will make you listen to a few more samples. And what I'm going to ask you, this is also selfishly, because then I will use your feedback to upgrade the model. What I will ask you is to try to describe, if you want to play the game, what do you perceive as a difference between the same tone recorded from a real piano and produced with our virtual piano. Okay, so there are 6 of them. I will play them very quickly, and then I would say we open the floor for discussion. Right, real piano playing a tone. Virtual piano, the same tone. Real piano, real piano, a chord. Virtual piano, a chord. A little scale. Real piano, same scale on a virtual piano. Sounds like a child learning to play, which is exactly what our model is doing. Thank you very much, and please, questions.